Okay, it seems that we can start.
Okay,
Okay.
great. So we're very happy to have John Novak giving our second talk, and he'll be talking about hypergeometric functions of huge random matrices.
Yeah,
Go for it,
that's right.
John.
Okay, so I'll pick up essentially where Colin left off. And basically, what I want to show you is that the spherical integrals that Colin was telling you about are part of a very big family of special functions, which are generalizations of classical hypergeometric functions. They're generally called hypergeometric functions of matrix arguments. And these objects were introduced by statisticians actually, and so they have a lot to do with probability, especially random matrix theory. And just in order to make sure you understand the spirit of this definition, I think it makes sense to start really with just classical hypergeometric functions. So this is a definition that goes back to Euler. So the hypergeometric series, it's a generalization of the geometric series. So if you just ignore whatever this is, I'll tell you what this is in a second. You just get the geometric series, right? 1 over 1 minus z. And what Euler did here was he put in coefficients, which are products of polynomials of a special form. Okay, so this x sub d is what's usually called the Pochhammer polynomial or Pochhammer symbol. Pochhammer came after Euler. He invented this notation, which is actually not the best, but it's the rising factorial. So x sub d is x plus one up to d factors, x plus d minus one. And so if you write this down explicitly, what Euler's hypergeometric series is, it looks like this. So it's 1 plus some d equals 1 to infinity. And this is the variable, z to the d. And the x's and the y's are parameters. They're parameters that in principle could be set to special values to give you special functions, which are generalizations of the geometric series. And you can see here, so this is product from c equals 0 to d minus 1. D is the degree. You have this product of ratios. So in particular, if the ratio of the dth term to the d minus first term is a rational function of the index d, which is the kind of the classical description of hypergeometric series, they're power series where the coefficients are rational functions of the degree, okay, which is exactly what is made manifest here. And so here are a couple examples. Like I said, the geometric series is the case where there are no parameters. Okay, so there's no x's or y's. It's just 1 plus some of the powers of z. And that's an exceptional example of a hypergeometric series in that you can actually sum it. Okay, so most of these things, the definition is there due to Euler, but actually evaluating the series is not going to happen in any kind of an easy way generically. So here's like an example which is like semi-explicit, you could say, is the binomial series, right? So I have one upper parameter x and my lower parameter is 1. And if x was equal to 1, you would recover once again the geometric series. And here x can just be any complex number, all right? So this series looks like this. So you have Pochhammer x for general symbol x, and it's this binomial series where if x is a negative integer, I guess, you are getting like the classical binomial theorem from, thousands of years ago. And if x is a positive integer, this is Newton's binomial theorem. And if x is anything else, this series is the definition of this symbol. Okay, so that's like one way to define what the complex exponential is. Okay, so certain special values of x, you can actually write down a formula for the sum of the series. And otherwise, all you really know is that for any x, it converges absolutely for absolute values at less than 1 to some function, and the name of that function is this. Okay, and an even more extreme example is the exponential series, which is a remarkable series which has lost many of its charms for us due to constant use. But this is the case where you have no upper parameter and one lower parameter equal to 1. So sum of z to the d over d factorial. And that converges absolutely for all z and c to a special function named the exponential function. And this really is a function that you don't know explicitly. Okay, but you need it. And so you give it a name. We call it the exponential function. You can't live without this function no matter what type of mathematics you do. For example, if you do probability theory, if you would like to define the characteristic function of a random variable x, you need the exponential function. You can't do Fourier analysis without it. Okay, so the basic message is that hypergeometric functions are hypergeometric series which do converge open neighborhood of z equals 0. And there's a kind of a rule of three here, which is very simple, whoops, which is easy to state, which is that the general hypergeometric series, when it's always valid as a formal power series, as long as the lower parameters are not integers, which are 0 or -1, are not non-positive integers. Okay, and the reason for that is you want to avoid division by 0 in this ratio. And as long as you stay away from that, you're fine in terms of formal power series. Okay, and if any of the upper parameters actually is an integer, a non-positive integer, this series is going to terminate. It's going to be a polynomial. And if that, because eventually you'll start hitting zeros in the numerator up here. And otherwise, so if you have a non-polynomial hypergeometric series, its radius of convergence is 0 if you have too many upper parameters. Okay, if the number of upper parameters is larger than the number of lower parameters, these coefficients grow too quickly, and you can't sum the series for any non-zero value of z. If the number of upper parameters and lower parameters are sort of perfectly balanced out, m equals n, then you get radius of convergence equal to 1, just like in the geometric series. And if the number of lower parameters exceeds the number of upper parameters, then actually the radius of convergence of this series is infinite, as in the exponential series, for example. And so there's this simple rule of three, which says that the radius of convergence of any hypergeometric series is either 0, 1, or infinity. And it really just depends on the difference between the number of upper and lower parameters and not on their values at all. And so what a hypergeometric function is just any holomorphic function whose Maclaurin series is a hypergeometric series is the way to say it. So, and these are typically functions which you can't write down in closed form, but until maybe even mid 1900s or something like that, virtually all special functions arose in this way. So if you open up any book on special functions like Andrew Zasky Roy or something like that, it's all about hypergeometric series and manipulations with them to try to glean information about special functions which are of interest, but that you can't actually write down explicitly. Okay, so that's classical hypergeometric functions. And so a natural question is, if all of the classical special functions, or most of them, are hypergeometric functions, what should we mean by a multivariate hypergeometric function? And there's several different approaches to answering this question. Some quite sophisticated, based on Lie theory, rather abstract. But there's one very concrete answer, which makes sense to discuss in a probability seminar, is that multivariate hypergeometric functions, their power series, which involve multivariate orthogonal polynomials coming from random matrix theory or used in random matrix theory. And the simplest version of this is to define a class of multivariate hypergeometric functions using the Schur polynomials, which are multivariate orthogonal polynomials, essentially for the circular unitary ensemble. Okay, so for the eigenvalues of a uniformly random unitary matrix. So if you are like an integrable probability person, this is your bread and butter. But if not, maybe it's not so familiar. So I figured I would go over it for a minute. So there's really the starting point of this definition goes back to Cauchy, which is if you just take any n by n matrix, complex matrix, Cauchy defines something called the bialternate, which is like a deformation of the Vandermonde determinant in the eigenvalues of this matrix. So it's S lambda of A. Here you have in the denominator you have the Vandermonde in the eigenvalues little a's of A. And then on the top, you have a kind of a shifted or deformed Vandermonde where you take the exponents and you add to them some other integers. Okay, so some non-negative integers, lambda 1 through lambda 1, without loss of generality, you can sort them in decreasing order. There's some non-negative integers. And then what you have is like a ratio of some antisymmetric polynomial in the A's by the Vandermonde polynomial, which divides every antisymmetric polynomial. So you're going to get a symmetric polynomial in the eigenvalues of your matrix A. And these are what Cauchy called bialternates. And today they're called Schur polynomials, universally, because they're the irreducible characters of unitary groups. And it doesn't matter so much if you don't know what that means. The important thing is that if you take two polynomials of this form, they're orthogonal with respect to Haar measure on the unitary group. So if you compute a matrix integral like this, so S lambda A, S mu A star, where you're integrating over A being an n by n unitary matrix, this is going to be equal to 0 unless these like two n tuples of deformations of the Vandermonde are the same. Okay, so that's the Schur polynomials. And okay, so this is just an example, just so you have some idea. Okay, I think probably everybody knows this. Normally you picture these parameters by which you're shifting the exponents in the Vandermonde as a Young diagram. Okay, so this is an example of a diagrammatic representation of some numbers lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, which are in weakly decreasing order. And this, there's a corresponding, so this is the Schur polynomial indexed by a Young diagram, which looks like a row of 2 and a row of 1 in 3 variables. And there's a combinatorial recipe for writing these things down. So this is the actual explicit expansion of this Schur polynomial. And what you do is you take this diagram and you are allowed to use the numbers 1, 2, and 3 because you have 3 variables. And you have to write those numbers in the cells of this diagram such that you are weakly increasing along rows and strictly increasing along columns from top to bottom. And that will give you the Schur polynomials. It's a very concrete thing. Instead of playing Sudoku in the morning, you can just write down Schur polynomials if you want. Okay. Um, and so the Cauchy identity is something that Cauchy proved using his bialternates, which we now today call Schur polynomials. And the right way to think of this identity is as a multivariate generalization of the geometric series. Okay. So for any complex number Z and any two n by n complex matrices A and B, which are satisfy this hypothesis, means that the absolute value of Z times the spectral radius of A and the spectral radius of B should be less than 1, right? So Z is just any complex parameter, and then I'm looking at the largest eigenvalue in modulus of A and the largest eigenvalue in modulus of B, and I want that to be less than 1. And what Cauchy showed is that this series converges, and not only does it converge, but it's explicitly summable. Okay, so it's absolutely convergent, and it converges to this product, which is a generalization of the sum of the geometric series, which is essentially the case n equals 1. Okay, if n equals 1, I just get the geometric series in Z times A times B, where there's only one little a and one little b. And so it's this product, ij equals 1 to n, 1 over 1 minus z, which is the geometric series, and then all possible products of pairs of eigenvalues of a and b. Okay? And so if you wanted to write down a theory of multivariate hypergeometric functions, what you could do and what has been done is that you take this as the geometric series, as the multivariate version of the geometric series, and then we just have to put some coefficients here, which are going to be some, products of ratios of generalizations of the Pochhammer polynomial from integers to integer partitions. And this is exactly what Alan James did in the 1960s. And James was a statistician, so he wasn't a pure mathematician. He wasn't an algebraist or anything like that. He came up with this definition because he needed it in applications in random matrix theory. And so this is what James called the hypergeometric function of two complex matrix arguments. And I'll just call it, okay, a function of two arguments is a kernel. So let's call it the hypergeometric kernel. It's a shorter name. So the hypergeometric kernel on n by n complex matrices, it's a multivariate power series that looks like it looks like a classical hypergeometric series, except with two matrices. All right, so GNZAB, these are the variables in this function, and x1 through xm and y1 through yn are parameters. And here is Cauchy's multivariate generalization of the geometric series. And then I just introduce these coefficients, which are defined in terms of these parameters, and some generalization of the Pochhammer polynomial. And that generalization of the Pochhammer polynomial is called the content polynomial of a Young diagram. So I'll show you a picture of what this means, but it's also quite likely that many of you already know what the content polynomial of a Young diagram is. This is like an example, one of the early examples in McDonald's books in McDonald's book in symmetric function theory. It comes up very early on in that subject. Okay, so the content polynomial is it's a very natural generalization of the Pochhammer symbol from integers to integer partitions. And what you do is you just write in the cells of your Young diagram the column index minus the row index. And if your diagram just has one row, that's exactly the Pochhammer polynomial. Okay, so it's if you have multiple rows, you're just getting copies of the Pochhammer polynomial where you're just shifting down by the row index. And this is the content polynomial of the Young diagram. It's just the product of x plus the content for every cell in your diagram, where the cell is the column index minus the row index. And that was James's definition of hypergeometric functions of two complex matrices or hypergeometric kernels on Cn times n. And so here's the definition written out a little more explicitly. So the coefficients is the product over all the cells in the Young diagram lambda, x1 plus the content of the cell up to xm plus the content of the cell, and then the same thing with the y's in the numerator, in the denominator here. And if your rank parameter n was equal to 1, you would just recover the classical hypergeometric series of Euler. And so this is really a power series in Z, and the eigenvalues of A and the eigenvalues of B. So it's not really necessary that you think of A and B as matrices, but it's good that you do. You should keep that picture in mind. But really, it's a power series in 1 plus 2n variables. And at least formally, it's well defined as long as your lower parameters are not integers less than n, just so that you avoid division by 0 in this denominator here. And the reason for that is that if you think about a Young diagram with at most n rows, the smallest content it can have is in the bottom left box, and that's going to be 1 minus n. Okay, so just to avoid division by 0. And if any of your upper parameters is an integer less than n, then this is going to terminate, and what you get is a multivariate polynomial. And then there's the question of what are the convergence properties of this multivariate series, and you might think that this is going to be somewhat tricky to answer. And in principle, it would be actually, but there is an amazing theorem again, these people are statisticians, Catry and Gross-Richards. They found a formula which expresses every hypergeometric matrix kernel in terms of the corresponding classical hypergeometric function going back to Euler. And so every series of this form is actually just the determinant of the corresponding rank 1 hypergeometric function. So this is like just G of Z, AI, Bj. So like this determinant is an n by n determinant where that's this n. And inside the elements of this determinant, you have the corresponding rank 1 hypergeometric function applied to each pair product of the eigenvalues, and just the parameters are shifted by minus n plus 1. So in principle, you have actually a formula for every series of this form as a determinant of univariate hypergeometric functions normalized by the Vandermonde in the eigenvalues of A and the eigenvalues of B. It's quite a remarkable identity, which is
Sorry, does this just come from writing the Schur polynomials as ratios of alternates and then just sort of taking the
yeah,
generating functions appropriately?
it does. So it's
Yeah, okay, that's
an
very
argument
cool.
of that form. And in fact, if you know how to prove the Cauchy identity in that way, you can do this.
Okay.
It's an elaboration of that. So it's like no coincidence that this is, Cauchy Binet type stuff. Okay. Yeah, exactly.
Thanks.
Um, and this tells you the convergence conditions for these series immediately as basically being inherited from the convergence conditions from just univariate hypergeometric functions. So, as long as each of your entries of your determinant is analytic, you're going to get an analytic function of several complex variables. And the required conditions are that uh, well, if m is less than n, each of these things is an entire function. So you're fine for any z and any matrices A and B. If m equals n, you need the product of the magnitude of z with the spectral radii of A and B to be less than one. And if m is bigger than n, the series is going to diverge unless every element of this determinant is actually a polynomial. Okay. Okay, good. So here's some examples, right? So the Cauchy kernel this is the Cauchy identity, okay, which we already discussed in just a slightly different form, right? So GNZAB is this multivariate generalization of the geometric series, and this determinantal formula is telling you that it's this determinant. And indeed, this is an equivalent form of the Cauchy identity, right? So this is something that's called a Cauchy determinant, and it actually is equal to the same product as in the Cauchy identity. It's for the same reason. Okay, um, you could talk about the binomial kernel on n by n matrices, which would be the natural multivariate generalization of the binomial series. So I have one upper parameter x, and my lower parameter is equal to n. And so it looks like this power series in Schur polynomials, where I have this generalized Pochhammer with any parameter x I want over generalized Pochhammer in n. And if I was to set n equal to 1, I would just recover the binomial series. Okay. And that is equal to this determinant. All right. And then there's the exponential kernel on n by n matrices, which is this series where there's no upper parameter and one lower parameter equal to n. And I just have 1 over the content polynomial of lambda evaluated at n. And indeed, if I was to set n equal to 1, this would just revert to the classical exponential series. And it is given by this determinantal formula, which you probably recognize from Colin's talk as being the evaluation of the spherical integral. It's exactly this determinant here. Okay, so that is how James defined multivariate hypergeometric functions of two matrix arguments. And here's like a little sample of what they have to do with random matrix theory. Since my working examples are really basically the binomial and the exponential, I'll tell you about those two cases. So the binomial kernel, what James found, right? So just to be clear, that's this series. Okay, so by definition, that's this series, and by theorem, that's equal to this determinant. And what James proved is that this multivariate generalization of the binomial has an integral representation as a matrix integral, an integral over the unitary group of rank n. And so it looks like this. So you're integrating over n by n unitary matrices against Haar measure, determinant of of I minus z au bu star to the power of x, where x can be any complex number. Um, and this looks quite a bit like a characteristic polynomial, right? So this is like the characteristic polynomial of a random matrix to the negative xth moment, and that's exactly what James wanted to use this for. And I'm going to elaborate on that in a second. And what Colin showed you in his talk is that the exponential kernel is given by this Laplace type integral over the unitary group, the spherical integral. And so let me elaborate a little bit on this identity proved by James, which definitely deserves to be better known than it is. It's a pretty remarkable thing. It's extremely well known to statisticians, but not that well known, not as well known as it should be to mathematicians. So here's a recent theorem of Marcus Spielmann and Srivastava, that they proved kind of as an outgrowth of this program where they basically resolved the Cadison-Singer conjecture using tools from random matrix theory. And something that comes out of their work is that if Xn and Yn are two independent uniformly random Hermitian matrices with deterministic spectra A and B, two real vectors, A, B, and Rn, then the expected characteristic polynomial of the product of these matrices, okay, which is this integral, determinant I minus Z AU BU star, can be expressed in a very succinct way in terms of the coefficients of the characteristic polynomials of each of xn and yn, which are non-random. Okay, so these are xn and yn only have randomness in their eigenvectors and not in their eigenvalues. Okay, so their characteristic polynomials are like this. These are the coefficients. ED of A is the elementary symmetric polynomial of degree D in the eigenvalues of A, and similarly for ED of B. And they proved that if the expected characteristic polynomial of the product of these two matrices is made up of the coefficients of the characteristic polynomials of the original matrices by this formula, which is called the Zago convolution of two polynomials. And that is just the case x equals -1 of James's formula. Okay, so it's there's a huge amount of information in this statement here, right? So if I set x equal -1, I'm getting exactly this integral. Okay, and the definition of this binomial kernel is this power series. And if x is equal to -1, this series terminates after n terms, okay? And you're actually only summing over diagrams with at most one row, and you're getting the elementary symmetric polynomials as the Schur polynomials here, okay? Okay, good. Most one column is what I meant to say. Okay, good. So that's one example of one of these hypergeometric matrix kernels, in action in random matrix theory. And so what, like, how many formulas like this are there? There are as many as you want. So it's a theorem of Colin and myself that every one of these hypergeometric kernels, as long as the integer parameters are, as long as the lower parameters are integers, can be expressed as a matrix integral over a product of unitary groups. And so the binomial kernel and the exponential kernel are just two examples of any number of integral representations of this kind. And in that sense, the definition of these hypergeometric kernels as power series and Schur polynomials is more important. Okay, so the matrix integral representations are in a sense, they're very useful, but in a sense they're special. And really, you should think about this as being the fundamental object that we would like to analyze. And if we can, then all of these matrix integrals become accessible. Okay, and that really is the main problem in this subject. It's a problem that's been around for a very long time in high dimensional statistics. And has made its way into mathematics and random matrix theory largely through exploration of things like the asymptotic behavior of spherical integrals or of characteristic polynomials of random matrices and that kind of thing. And the main problem is, how would one go about? So like I said, even for n equals 1, when these are classical hypergeometric functions, generally you can't write down a formula, okay? For arbitrary rank n, you can write down this series as a determinant involving classical hypergeometric functions, which doesn't really help you, right? Because it's an n by n determinant, as Colin was saying. And the question is, can you find some way to approximate all special functions in this class of multivariate special functions as the number of variables goes to infinity. And this is a problem that's been around for quite some time. And until relatively recently, it was just not at all clear what one would expect an answer to this thing to look like. Just even as a conjecture or any kind of guess what the form of these asymptotics might be was essentially unknown. And the main insight that I want to impart to you today, if there is one, hopefully there is one, is that this question is equivalent to computing the asymptotics of the partition function in a model of random Young diagrams. Essentially, is the way to say it. And so this is a translation of just a problem in high dimensional analysis into a probabilistic type of question. And the virtue of this of making this translation is that there are analogies which tell you what you probably ought to expect to happen as n goes to infinity. So I'll explain that to you. I'll explain that to you now. So let's see. Let's see. We would like to determine the asymptotic behavior of this multivariate special function as the number of variables goes to infinity. And what I'm going to do is I'll let the parameters of this function scale linearly in the rank. Okay, this is a regime where you're going to get some non-trivial n to infinity limit. And, I mean, the reason for this is that you don't, if I didn't make this, okay, so let me just show you in the computation, right? So if I let, so these are just some fixed parameters, u1 through v1 through vn. And the reason they have inverses will just come out in this calculation right now. So I'm letting these parameters of my multivariate hypergeometric function grow linearly in n. And so this is what the coefficient looks like. And what I can do is I can just pull out each of these factors, right? Just take them out. And what I get is something which is going to like stabilize as n goes to infinity, right? So like each of these things is going towards one, but of course, like it depends how they're going to interact with each other. And I just get a bunch of, it's just a renormalization, right? I get a bunch of these, I get z times v1 through vn over u1 through um. And then I have like a scaling, which is n to the m minus n, because there's m copies of the rank parameter up here and little n copies of the rank parameter down here. And I just absorb that into z and call that a new variable q. Okay? So this is the right normalization of hypergeometric kernels to look at the n goes to infinity limit. Okay? And you can think about this probabilistically. So I'll define the hypergeometric distribution on yn. So this is the set of Young diagrams with at most n rows. It's going to be a unit mass complex measure whose mass function looks like this. So it's a probability distribution on Young diagrams lambda with the most n rows. And the weight that is assigned to a given Young diagram is the corresponding Schur polynomial in some parameters A, which I like to think of as the eigenvalues of a matrix, and Schur polynomial in the eigenvalues of another matrix B, and then product over the cells of lambda Q, where Q is just really a parameter, which in a sense is redundant because you could just stick it in with either A or B if you wanted to, but it's useful for keeping track of things. And then V is a potential. Okay, and that potential is a rational function. Why rational? Because this is coming out of because it's hypergeometric, because of the way we defined it. So V of zeta is just any ratio of two polynomials with constant coefficient equal to one, where like the degree of the numerator should be at most the degree of the denominator, so that the partition function, which makes this thing into a unit mass measure, actually converges. All right, it's going to be exactly this. Okay, and so probably at this point will help to have an example of what such a distribution on partitions looks like. And here's the simplest example. So if your potential V is the constant function equal to 1, you get an extremely well-known distribution on Young diagrams. And this is a Kunkov's Schur measure. Okay. So okay, it's called the Schur measure, but really what it is it's a multivariate generalization of the geometric distribution, right? It's the if n is if your rank parameter n is equal to 1, this thing, as we discussed, is just the Cauchy identity, is just the geometric series. And so like this is like the probability distribution on non-negative integers, which just gives, mass z to the d to the integer d. And we're doing that for diagrams lambda instead of integers. And the partition function is given explicitly by the Cauchy identity. And so this is as long as, let's see, as long as the modulus of Q times the spectral radius of A times the spectral radius of B is less than 1, this is a well-defined unit mass complex measure on Young diagrams with the most n rows. And if, let's say, A star equals B, then this is actually a legitimate positive measure, probability measure on Young diagrams. Okay, and if Q is bigger than or equal to 0. So here's another example where the potential is non-trivial. So V of zeta, instead of being just equal to 1, it's the rational function 1 over 1 plus zeta. Then I get this probability distribution on Young diagrams with the most n rows, which is really the multivariate version of the exponential distribution on the natural numbers, on the non-negative integers. Okay, and the partition function there is this spherical integral. Okay, so you have the Schur measure with this potential, with this weight added into it. And so this is a huge, yeah, okay. So this is a basic remark. So if your potential V is positive on -1 to infinity, this hypergeometric distribution on Young diagrams is going to be a bona fide probability measure for any choice of parameters A and B, which makes the Schur measure a bona fide probability measure on diagrams. So it's a very well-behaved class of deformations of the Schur measure, and a very natural one about which not much is known. And estimating the partition functions for this class of models is the same thing as estimating hypergeometric functions of matrix arguments as the rank parameter n goes to infinity. And so this is just a translation of the original problem, but it really helps you to get organized in terms of like understanding what you might hope for. So what we're dealing here with is ensembles of random Young diagrams against an exactly solvable background measure, an integrable background measure, which is exactly the Schur measure, right? So this piece here is Schur measure, and then I'm just putting in a potential. And this is very much like the situation that you encounter in random matrix theory, where you look at probability distributions, let's say on n by n Hermitian matrices, against an exactly solvable background measure, which is typically the Gaussian measure, where you can just write down anything you want. And then you add a potential. And if you're really brave, you also add an external source. So this is like the most general version of the Hermitian 1 matrix model. And then you go from here, right? So then there are two ways which one might go. So in random matrix theory, you take your deformed exactly solvable model, and you either try to understand statistics of the eigenvalues in this model. Okay, that's one main objective of analyzing the Hermitian 1 matrix model. And another major direction of research focuses on what is the asymptotic behavior of the free energy in this model. In other words, the asymptotic behavior of the logarithm of the partition function. And there's a huge amount of work that has gone on in both directions here. There's universality of the local statistics in very general Hermitian matrix models like this. And the other is, what is the asymptotic behavior of the partition function for an arbitrary potential V? And in various degrees of precision and rigor, it's known that the partition function emits a n goes to infinity asymptotic expansion, starting with leading order n square and going down in powers of n to the -2 from there, whose coefficients are some analytic functions, okay, in this parameter q and also in the eigenvalues of the external source, which have a topological interpretation in terms of maps and things like that. I won't really go into it. And it's the same thing here, right? So we have this class of hypergeometric distributions on Young diagrams with at most n rows. We're thinking about that like n by n matrices, okay? And we can either ask about spectral statistics in this model of random Young diagrams. I'll tell you what that means in a second. Or we can ask about the asymptotics of the partition function, exactly as in random matrix theory. And this question of what is the high dimensional behavior of hypergeometric functions of matrix arguments is exactly the latter question, right? Okay, so in terms of the spectral statistics, okay, I think probably everybody knows this picture. Like, I mean, I imagine this is like on the street signs in Moscow or something at this point. It's like you can't escape this. All right. So there's a way to talk about something that's analogous to eigenvalues of a matrix for Young diagrams. And what Akunkov did when he introduced the Schur measure was he solved that problem in the case where there is no potential. Okay, that's why I'm calling it this exactly solvable case. He wrote down, not basically, he did give a formula for the correlation functions of this point process when your diagram lambda follows the Schur measure. And a very interesting question would be to do the same when you have this potential here, which is just some rational function evaluated on the normalized contents. And what is do you still have a determinantal point process? And if so, what is the kernel in terms of the parameters which define the potential? And I strongly suspect that's a question that can be answered, but that's not the question that I want to answer. But rather, the question that I'd like to address is the global type one, which is what is the asymptotics of the partition function in these hypergeometric models of random partitions? And is there a topological expansion? Okay, I can see I haven't budgeted my time all that well. But just in the case, once again, in the Schur measure case where your potential is trivial, this is trivial because this is just the Cauchy identity. Okay, so this is one way of writing down the Cauchy identity is basically that you're as an exponential function. So logarithm of the free energy, right? So this is something that's summable from the Cauchy identity is in fact equal to n square f0q as a finite n identity. So there's no need to take n going to infinity or anything like that, where f0q is just this this logarithmic function, so q to the d over d, and pd of a and pd of b are just the sum of the power of the dth powers of the eigenvalues of a and b, and this is a convergent series. This is one way of writing down the Cauchy identity. And there's the analogy with random matrix theory allows you to kind of do what people in multivariate statistics were trying to do, which is to sort of like guess what should the behavior of these multivariate hypergeometric functions actually look like in the high dimensional regime. And the guess to make is that there is a topological expansion of the partition function, which kind of mimics something happening in the continuous version of random matrix theory. It's like a discrete version of that whole program. And so just to be a little more clear about what this is, so you're hoping for an asymptotic expansion of this form, okay, which is what you see in random matrix theory, where the coefficients of this expansion should be analytic functions, okay, in the in the moments of the spectral measures of the external source matrices A and B, which is exactly what this was written down here. So P alpha and P beta are power sum symmetric functions with some coefficients which should have some enumerative meaning. Okay, some numerical coefficients which are somehow related to like combinatorial topology. And so at least you can guess that this is what should happen. And nowadays there are very precise guesses as what should emerge from this, namely that this topological expansion should exist for all these hypergeometric distributions on Young diagrams, and there are explicit candidates for what the free energies in these expansions should be. And there's certain Hurwitz numbers or generalizations of Hurwitz numbers, which maybe I won't go into, and I'll just tell you what is done. So basically, it's following the same genesis as what happened for partition functions of matrix models. First, people guessed, like in physics, non-rigorously what these topological expansions ought to be. And as far as physicists were concerned, that was typically good enough, right? They didn't care so much about whether things were convergent or not. And that's where we're at with this right now. So this conjecture is formally true. So the first step in this direction was that it was formally true for this specific potential V of zeta is 1 over 1 plus zeta, which corresponds to the spherical integrals that Colin was talking about. And where we're at now is that the conjecture is true analytically, both for that potential and a slightly more general one, which corresponds to these rectangular spherical integrals that Colin also briefly mentioned, which are like Dyson-Brownian motion for rectangular matrices, like what Roger asked about. So this is done, and there's also at least formally, the conjecture is true for arbitrary potentials. So there's a guess for how these expansions should look where your V could be any rational function that you want. And this has not yet been confirmed analytically, but as the saying goes, if this turned out to be false, I'd eat my hat. I mean, I think it's that's going to work out eventually, but it's a question of overcoming various analytical obstacles to get there, just like in partition functions of matrix models. Okay, and then maybe I'll just use my last minute to tell you about a very interesting kind of extension modification of this program. So here's a little a palette cleanser, which is you just forget about everything I said before. And let me just ask you a little trick problem, which is suppose you have the eigenvalues A1 through AN of a uniformly random unitary matrix, so the circular unitary ensemble. What is the expected value of this random product? Okay, so I'm looking product from ij equals 1 to n, and there should also be whoops. All right. What's the expected value of this random product? A little pop quiz. And this is just a Cauchy identity again. All right. So if I was to expand this thing out, this expectation is with respect to Haar measure. And sure orthogonality just says that these two factors go away. Okay, this just becomes 1. And so what I'm getting is just the number of Young diagrams with D cells and most n rows summed over all D. And that's just Euler's partition function for the number of partitions of with at most n parts. Okay. And so there's a way to make Schur measure disordered in a very kind of canonical but interesting way, which is so people are doing all kinds of stuff with Schur measure where they take the parameters A and B and they specialize them in various crazy ways to try to make Schur behavior exhibit pathological behavior of various kinds. Another thing you could do is take a random specialization of Schur measure and see what happens there. And so Schur measure with CUE disorder is a random measure on Young diagrams with at most n rows, where the mass function is just the modulus of the characters of the unitary group at uniformly random inputs. And then the partition function becomes a random variable whose expected value we have just computed. And so you can do this for also add back in the potentials. So hypergeometric functions of the CUE are random analytic functions where you just take your A's and B's to be a uniformly random matrix and its conjugate. And this is a very interesting new class of observables of the circular unitary ensemble in random matrix theory, which is, let me just show you what happens. Okay, so the hypergeometric distribution on Young diagrams with CUE disorder is exactly what we have discussed previously, except for A and B, you take a uniformly random unitary matrix and its conjugate, and what you get is a random measure on Young diagrams with the most n rows, whose partition function is a random variable of this form, a random analytic function of this form. And there's an analogous conjecture for how this thing should behave in expectation, which is that so now we're dealing with a disordered system, right? So you take expectation of the partition function and then logarithm of that. This would be the annealed free energy in this disordered model of random Young diagrams. And here the conjecture is that the genus expansion actually starts not at genus G equals 0, but at genus G equals 1. And so its leading order is not n square, but constant. And that makes perfect sense because essentially the eigenvalue repulsion in the CUE this is a phenomenon you see everywhere for statistics of random matrix models. The eigenvalue repulsion is going to force various statistics to be smaller than they otherwise would be due to a lot of cancellation. And so you're getting leading order constant instead of n square. And that leading order is exactly computable. It's the logarithm of Euler's generating function for Young diagrams with a given number of parts. Okay, and so the recent work is that this disordered conjecture for hypergeometric functions is formally true for all potentials. And moreover, the coefficients in this genus expansion are actually quasi-modular forms. They're polynomials in Eisenstein series of even weight, which for except for E2 actually are modular forms. And this is a kind of a brand new connection between random matrices and number theory, which is quite surprising. And in this disordered world, what is known is what has been done so far is that for the special potential V of zeta is 1 over 1 plus zeta, this is analytically rigorously correct. Okay, so the expected partition function, which is like a double spherical integral, where you integrate over, like instead of AU BU star, you have AU A star U star, and you're integrating over two copies of the unitary group. This actually does admit a topological expansion starting at genus G equals 1, whose orders are quasi-modular forms. Okay, and okay, so obviously I guess I rushed a little bit in the end, but maybe I'll just stop there because I'm already 5 minutes over. So that's the story.
All right. Thank you very much, John. That was very cool. Let's thank John. Um, so okay, anyone want to jump in with a question before I jump in with a question?
Yeah, maybe I have one.
Sure. Yep.
So is there a chance that the last thing you told us, there a chance that the quenched free energy is equal to the annealed in this case?
There is. Yeah. I mean, there is that chance, and I think it's. I mean, I hope so. Yes. But I can't tell you for certain either way.
But one way in this kind of cases is to try a replica method. That is, you take expectation of z square, z cube, etc.
Right. Right.
That would still be in the range of this kind of complicated hypergeometric things.
Yes. Yeah. Yes, that is definitely something that would be a something reasonable to try. Um,
You would just have
I don't want to stick my neck out
and
and make a prediction that I can't. But yes, that's exactly the type of thing that one will try to do.
okay,
Yeah,
thank you.
yeah.
Wait, to make sure I understand, so you think that there's a good chance that the quench free energy, which a priori is random, is actually a deterministic function of these CUE eigenvalues?
Well, so let me show you where.
Maybe I misunderstood what the statement was, but to me at least that sounds surprising.
Yeah. Um,
Usually in this kind of cases, you do have concentration, and
yeah.
so
Yeah.
Oh, so you don't mean deterministic at finite n, you just mean at
No,
concentrate.
not at
Oh,
finite end.
okay,
No,
okay, okay, okay.
definitely not at finite end. No,
Yes,
definitely not.
okay,
Yeah.
okay. That's why I was so surprised. Yeah, okay, okay.
Right.
Then this is
Yeah.
very clear to me.
So I mean, I'm trying to find where I put this conjecture. Yeah. Okay. Yeah. Yeah. It's exactly here. So I mean, to Gerard's question. So what you're basically seeing is that the annealed free energy is converging as n goes to infinity, and the first order term in this expansion actually does not depend on the potential. It's always the logarithm of Euler's generating function for integer partitions. And so what this suggests is that every hypergeometric distribution on Young diagrams with CUE disorder is actually converging as n goes to infinity in Haar measure, in Haar probability, to a deterministic measure, which the natural prediction is it's the Q uniform measure on all Young diagrams. Okay, so just the measure um, which gives every Young diagram mass proportional to Q to the number of cells, and that's sort of what this universality of this first order term is predicting. And if that's true, then the quenched and annealed would be the same.
but in fact, you would have to prove the quench equal annealed before proving the conjecture, obviously.
Say again, I'm sorry.
In fact, you would have to prove that quench equal annealed before. That's why I was asking before
Yes,
proving the
yes,
conjecture.
yes,
It's
right.
building
I
blocks.
don't know how to prove this conjecture.
Uh,
It's just
okay.
what would make sense.
So experience from spin glasses. Take expectation of z square, z cube. That's do like Parisi told us to do.
Okay, I'll do that.
Sorry,
Yeah.
but it
Yes,
kind of
I agree. I
can
agree.
work.
That's
It says
that's the thing to do.
it worked for spherical spin glasses in the work of Subag, so
Yeah,
maybe it will work here. But
yeah, yeah,
okay.
yeah. No, I absolutely. Um, yes, I hope I can do that.
Um, if so, I see a couple of raised hands. If there aren't any sort of follow-up questions to that, if there are, just shout them out. Otherwise, I think Zikicha Lukic. I'm probably butchering your name. I'm
Uh,
sorry. You raised your
yes,
hand.
yes, no problem. Can you hear me?
Yes.
Oh, so I'm a statistician, and my question may be a little bit off topic,
Okay.
but have you considered approximating the hypergeometric function by James? For example, just continuing the work of Butler and Wood, which used the Laplace approximation in your more complex scenarios.
I have
So
looked at the paper of Butler and Wood, and I what I can tell you is that it's interesting work that they did, but the problem is that, and this is really the split between what I'm talking about and what people were. So in the time of James and statisticians, Muirhead wrote a big book on multivariate statistics, which has these hypergeometric functions as a major component. For them, n was arbitrary but fixed always. And that's what they meant by multivariate statistics. They didn't mean high dimensional statistics. They meant multivariate with an arbitrary but fixed number of variables. And these approximations, these Laplace style approximations of Butler and Wood, are in that regime. So they're basically for when the parameters in your hypergeometric function tend to specific values, but your n stays fixed. And they have good approximations there. Um, and the type of method that they're using basically can't work when you let n grow. So I did look at what they did, and I think that it is not applicable to the high dimensional regime for these hypergeometric functions of matrix arguments for exactly the same reasons that classical Laplace approximation is not applicable to large n asymptotics of, say, Hermitian matrix integrals. They're just different worlds. So I think that the answer to your question is no, it can't work that way.
Okay, thank you very much.
Yeah.
All right. So it looks like we also have a question by Andre.
Thank you. Thanks. Both talks were quite fascinating. It's a more general question. You mentioned during your talk, Jonathan,
Uh-huh.
several complex variables.
Mhm.
How would this analysis look, say, in terms of kernels? You have, say, Go-Bergman and so on. Could it be extendable from one complex variable to several complex variables?
So I suppose that you can tell me if this isn't exactly what you are asking, but it's already several complex variables
Mhm.
in the following sense. So this conjecture, which as I said is known for certain specific potentials, let me be a little more precise about what is meant in this asymptotic expansion here. This is a n to infinity asymptotic expansion, means that, if this is a divergent series, but if you stop it after finitely many terms, the error is going to zero faster than the exponent of the term at which you stopped. And this
Mhm.
estimate is uniform over modulus of q times spectral radius of A, spectral radius of B, sufficiently small, depending on the potential. So really what this is saying is that this expansion is holding in a open neighborhood of the origin in complex space of dimension 2n plus 1, where one of those dimensions is Q, and n of them are the eigenvalues of A, and n of them are the eigenvalues of B. So this is actually a statement about the asymptotics of a analytic function of 2n plus 1 complex variables as n goes to infinity. So in that sense, it's already happening in several complex variables. Um,
Mhm.
and so is that is that the spirit of your question?
Yes, yes, sure,
Yes. Okay.
sure. Basically, so, but this could be translated to all of the analysis that you had. I mean, the
Yes.
extension to CN.
Yes. Yes. That's correct. I mean, uh, but I just want to say, just so that we don't, when I went over to this kind of disordered version of the question,
Mhm.
now this becomes univariate. We just have one parameter q because
Mhm.
these other variables, the a's and the b's, have been taken to be random. Okay, they're the eigenvalues of a uniformly random matrix and its adjoint. Um, but yes, in the non-disordered case, this is all about analytic functions of 2n plus 1 complex variables as n goes to infinity.
Thank you. Thanks.
Yeah.
Are there any other questions? Okay, so I was curious, do you have any guesses about the probabilistic behavior of these, CUE randomized Schur measures? Like, maybe it's not exactly clear what are the right questions to ask, but have you thought about
Yeah.
this? Do you have guesses what's true, even if you maybe don't know exactly what's true?
Right. So the the first guess that I have is this one, which is that there's a law of large numbers. So
Hmm.
let me just forget about the potential for a second, and if you can just if you know how to answer this, I would love to hear the answer. But suppose I just take Schur measure. Okay, it was a
Hmm.
very, very familiar object. I take Schur measure, and for its parameters, I take the CUE. Okay,
Hmm.
that's a random measure. Does it actually converge in hard probability to a deterministic limit? And that's what I'm saying happens. And what I'm saying, moreover, is that the law of large numbers is actually Q uniform measure on all Young diagrams. So that is the simplest probabilistic phenomenon which I'm basically predicting. And I don't know how to prove that. I haven't
Well, that's
really.
interesting because if you took
Yeah,
fixed specializations, then this Schur measure would sort of belong in the world of like a 1D slice of a 2D random tiling, and you would see like GFF style fluctuations, for instance. Whereas for this like single Q to the volume partition, that's not what you see.
right.
Or,
Yeah.
so you're saying that somehow the like this is sort of interesting to me. Like the randomness of the eigenvalues kind of averages you out of the 2D random height function situation into the
Yeah.
1D random height function situation.
That's exactly what I think. I could
That's
be totally wrong,
fascinating.
but I don't think I mean I think that's yes. I mean I think that's correct, and at least at the level of expectations, it's correct. Um,
Hmm. Right. Which,
yeah.
that's some indication.
I mean,
Okay.
actually, so I mean, another thing I didn't talk about, you can do all of this at arbitrary beta, right? So
Mhm.
these hypergeometric functions of two matrix arguments, McDonald defined them for arbitrary beta, just replace Schur polynomials with Jack polynomials.
Sure.
And so, the question really is, suppose I take Jack measure, right, which is exactly Schur measure, except with the Jack polynomials, the arbitrary beta,
Hmm.
and I make it disordered by putting C beta E, okay, by putting the circular beta ensembles in. You should get a law of large numbers in which the distribution, irrespective of beta, is Q uniform on all Young diagrams.
Huh.
Uh, I don't know how to prove that, but at least it's true in expectation.
Huh.
So I think
Interesting.
this really has not been done. Like people have been looking at how to take very specific deterministic specializations of Schur and Jack measures and tune
Right.
them in all kinds of crazy ways to produce exotic behavior. And another thing you can do is to make these measures random and driven by random matrix statistics.
Yeah,
And
no, I agree. It's an
well, that
extremely
hasn't been done,
useful
I
thing
don't think.
to
Yeah.
do. Yeah.
When you think about it, it's a very natural thing to do because these are all orthogonal polynomials for random matrix eigenvalue distributions anyway. Uh,
Right. And
it's
and we
it's
use
it's
them to become
analyzable.
random
Yeah.
matrix eigenvalues, but we don't sort of flip
Yeah,
that on its head and use the random
exactly.
matrix eigenvalues to drive the
Mhm.
random partitions.
Yeah, and I mean, at least at beta equals two, what's sort of amazing from a maybe more algebraic point of view is that what comes out of this are quasi-modular forms, which
Right.
are associated with uniform distributions on Young diagrams. So things
Mhm.
are matching up as they should. Uh,
Yeah, right.
yeah,
So like the for just the Euler partition function, you get the Dedekind eta function, if
that's
I'm
correct.
remembering
Yeah, yeah,
correctly. And you can actually sort of use the modularity of the Dedekind eta function to prove things you want about like asymptotics of Q Pochhammer symbols. And so
that's
you
right. Yeah.
and so you have some sort of story for the similar, or at least one could have some similar story for the higher order corrections as well, with like, good asymptotics as Q goes to one or something like that.
Yes. Yep.
Okay, that's very cool. Um, maybe another follow-up question. So this um, is is there a way that you could get so here when you're doing this averaging over Schur parameters,
Hmm.
sort of ended up with something which looks like a 1D random partition rather than a slice of a 2D height function. Is there any way from this framework that you could get a random 2D height function with random background?
I haven't looked at that at all. So I mean, you're basically asking about like what is a disordered Schur process?
Yes, that's exactly what I'm
Yeah, right.
asking.
Yeah, I mean, these
And
are
once you get skew Schur polynomials in the mix, yeah, I sort of have no idea how things would work.
yeah. This is all pretty new stuff, and I haven't gone there yet. I mean, it's definitely
Mhm.
something that's in my mind as something to look at, but I don't have anything. Um, where I'm at is the question you just asked.
Mhm.
Yeah,
Okay.
yeah.
Okay. Um, okay. Think I think that's everything I wanted to ask. Does anyone else have any other questions? Okay, so let's
Okay.
let's end the recording here, Luis.